In this presentation, we report about the work carried on by our team at the University of Alicante about the effects of the dart impact on Dimorphos, which is the secondary of the Didymos system. I am Adriano Campo Bagatin, and I will introduce the problem and main assumptions. Paula Benavides will talk about the research methodology and results on spin and axis change. Finally, Poi and Liu will tell you about results on the energy reaching the surface and possible boulder motion. According to NASA plans, the DART spacecraft shall impact Dimorphos in early fall 2022 at a speed around 6.5 kilometers per second. This shall likely be a cratering event at hyperspeed. In such impacts, most of the impact kinetic energy is dissipated into melting, vaporization, rock deformation, heat transfer, and so on. That means that only a small fraction of the impact energy goes eventually into kinetic energy of the target. So, kinetic energy is not conserved, but both linear and angular momentum must be conserved in the system. Then the evolution of early post-impact dynamics of Dimorphos and the response of its internal structure to the impact both depend on propagation into the target of linear and angular momentum and propagation of the residual kinetic energy. And this is in fact our motivation to study this system. In this study, we do not analyze the shattering phase itself. Instead, we only consider the kinetic energy of the collision that is finally delivered to the target. There is little information about the quantitative fraction of kinetic energy that we call FKE that still reaches the target beyond the shattering phase. This is sometimes estimated from catastrophic disruption experiments in a range going from 1 to 10%. In the case of cratering experiments, we make reference to the work by Walker et al. 2013. That was a hyperspeed cratering shot onto a concrete sphere of 1 meter size. The sphere was mounted on a frame and it was displaced in horizontal and vertical direction by the impact while pivoting about one of the edges of the frame. We estimated a fraction of 0.25% of kinetic energy going into the target for FKE. This may be somewhat an underestimation of the energy going into the target. In fact, part of the energy may also be absorbed by the frame itself. Now, when modeling this kind of system, we face the problem of suitably scaling the mass and speed of the real projectile, that is, the DART spacecraft in our case, to the mass and speed of our synthetic projectile. Now, this scaling has to meet the constraint that the linear momentum must be conserved, but only a fraction FKE of the DART impact energy will be transferred to the target. So, opposite to reality, our synthetic projectile will not be destroyed by the impact. It will just rebound on our synthetic Dimorphos. So, in order to do the scaling properly, this must be taken into account in the equations. So, we must consider the fact that the synthetic projectile after collision will take away energy, and it has to deliver a fraction of that energy to the target. Also, we must consider the momentum taken away by the synthetic projectile in the equation below, so that the remaining momentum corresponds to the real impact momentum that has to be conserved.
We investigated the possible reaction of Dimorphos to DART collision under the assumption that it is a gravitational aggregate. We performed numerical simulations using the soft field discrete element n-body numerical code from Schwartz 2012 to study the dynamical evolution of components when the shattering phase is over. At this time of study, Dimorphos is not present in our simulations. Regarding to the model assumptions, we assumed 5 different impact geometries as characterized in this figure. In the left plot, I show a view in the x-theta plane. Here, R1 is a head-on collision that passes through the center of Dimorphos. R2 and R3 are similar to R1, but its impact direction passes through the half of the radius distance. And then R4 and R5 are shown in the XY plane. These are equivalent to R1, but with a y-axis offset impact direction of plus and minus 15 degrees. We scaled the actual dart velocity and mass and considered a Dimorphos reference model for size, density, and initial spin period. We also used the conservative value of the restitution coefficient for interparticle collisions of 0.3, corresponding to air rock values. Here, I show another schematic view of the impact geometry, and as the very structure of Dimorphos is unknown, therefore we model it by a different way. In our case A, we considered a monodispersed distribution of the particles, of spherical particles. We considered about 100,550 equal spherical particles. And then we considered 2 cases with multidispersed particles, one with high resolution. We considered 100,000 particles, which radius go from 1 to 0.5 meter. And then we considered a low resolution case with about 13,643 particles, with radius go from 1.9 to 4.8 meters. We are also working at this moment on simulate targets made of irregular components. Here I show a typical impact. Okay, so here I show the first part of our results, where we analyze the change in the spin period, the axis orientation, and the direction on the angular momentum. As you can see in this plot, only the R5 impact geometry tend to increase the period, while another impact geometries tend to slightly decrease and stabilize about 11.7 hours, which means a change in the approximately 12 minutes. Regarding to the spin axis, we can see that depending on the impact geometry, the spin axis can change between 0.14 to 1.8 degrees. The last plot shows that angular momentum vector is stabilized quickly. No precession is evident at this stage, even if the slight inclination of the spin axis implies that tidal torques due to the primary may alter this situation secularly.
Moving on to the second part of our results about the impact effect on the surface of Dimorphos, Here we show the kinetic energy distribution of the borders on the surface of Dimorphos at 3 seconds after the impact. The phi and theta angles are longitude and latitude as the plot on the left illustrated. At this point, the energy from the impact has already propagated through the body and reached the surface, causing minor shaking of the regulus. The black curve is the impact plane represented on the phi and theta coordinates. The energy distribution seems to have a very weak, if any, preference for the impact plane. The two purple regions with the highest energy are the energetic ejecta directly caused by the dot impact. However, we would like to focus more on the propagation of the energy to the surface away from the impact region. Therefore, we calculate the horizontal displacement of all the borders on the surface at the time when the whole system has reached a dynamically stable state, which is about a few tenths of minutes after the impact. In this plot, we show the borders that can have horizontal displacement larger than 10 centimeters, and we artificially remove the borders near the impact region for the aforementioned reason. We found that the largest horizontal displacement is about 4 meters, but most of the surface borders only migrate for 0.5 to 1 meter. The number distribution of the horizontal displacement of the borders selected in the previous plot is shown here. 96% of the selected borders have horizontal displacement smaller than 1 meter, and the mean horizontal displacement is about 0.59 meter. And here we show only the borders that can have horizontal displacement larger than 1 meter. Only about 140 borders of that size are found in this displacement range. And then we show the horizontal displacement of the surface borders as a function of time within 4 minutes after the impact. The Lysia CubeSat, which is in charge of monitoring all effects of the impact, will start taking pictures 3 minutes after the impact. And the camera resolution on board Lysia CubeSat is about 1.5 to 3 meters. As shown in the plot, the largest horizontal displacement is only about 1.4 meters, which is below the best resolution of the camera. Therefore, our result shows that the Lysia CubeSat will be observing essentially the original locations of surface borders. So, by comparing the pictures taken by the Lysia CubeSat to the ones taken by the higher resolution camera on board the Hera spacecraft, we may be able to check if horizontal displacements of borders took place and how much our model is consistent with spacecraft observation. In summary, first we present 3 numerical impact experiments performed on Dimorphos synthetic target. One monodispersed sphere distribution with 100,000 particles having fixed radius of 1.5 meter, and then 2 multidispersed sphere distribution, one with 100,000 particles with a radius range between 1 and 2.5 meters, and the other with 13,500 particles with a radius range between 1.9 and 4.8 meters. We scale the kinetic energy transferred into the target as in Walker et al. 2013 cratering experiments. And then we reported results for case B. We found that the spin period and axis orientation change depend on impact geometry. We found a spin period change of up to 12 minutes and spin axis change between 0.14 and 1.8 degrees. No precession of the spin axis is observed. Regarding the effects on the surface, we see that the residual impact energy will reach the surface, causing boulder motion limited to 4-meter displacement, which is potentially detectable by comparison of Lycia and Hera observations. Our future work is to include Didymos mass in the simulation and explore the range of the fraction of impact kinetic energy delivered to fragments, and then apply irregular shape components and size distribution to non-spherical target shape. Thank you very much for listening.